Okay, guys, so in this video, I'm going to talk about 7.1, which is integration by parts. Now, as mentioned in the 5.5, the U sub, basically all integration that we deal with involves either U sub or integration by parts. So those are kind of the two fundamental methods that we need to have kind of mastered under our belt. Now, most students will find that they prefer integration by parts because it follows a nice formula. Um, but for me, I always preferred U sub. And in fact, the second I left Calc 2 originally, I like immediately forgot integration by parts because, to be honest, I use U sub a lot more than I ever did integration by parts. Um, so that isn't to say that you aren't going to use it, because you will, but I obviously went long enough between integration using integration by parts that I kind of lost it. But it is a very important thing to know. So first of all, let's talk about kind of some basics. Essentially, differentiation rules generally have like opposites, right? So the substitution rule, U sub, corresponded to the chain rule, and integration by parts corresponds to product rule. Okay, so essentially, if you recall, your product rule was the derivative of f of x times g of x is f prime g plus g prime f. Okay, so that means that the integral of f prime g plus g prime f must be f times g. And so doing a little bit of rearranging, essentially what we do is we split this integral into the two sums, and then we solve for this one here. So the integral of g prime dx f of x here, so this portion here, is equal to f of x g of x, so this right here is here, and we subtracted this one over, so minus g f prime x dx. Now, the reason we are rewriting them in that order is just because it's going to follow the order of our U sub formula, not U sub, excuse me, integration by parts. So essentially, we get this. We often describe them in terms of U and V. Essentially, f is U, g is v, and so plug it into our formula, U dv is equal to uv minus v du. And this is our formula for integration by parts. Now, in general, we have to choose a u and we have to choose a dv. Sometimes one of those things is just a simple like 1, but oftentimes it's a function of x. So one of the things to keep in mind is that essentially we want to choose the one that's a u because going back to this, essentially, we will choose a u and a dv in our original function. We will derive u to get a du, and we will integrate dv to get a v. So the thing that derives our u is the thing that we want to choose that it will simplify as we derive it. So if you think sine, the derivative of sine is cosine. That's not going to simplify. But if we derive x, it becomes 1. That does simplify. So in general, we choose our u to be the one that simplifies as we derive it. So that is to say, u is x, and our dv is the rest of it. So that is sine x dx. Now, a couple things to note is that, first of all, my u's are like this. So again, the integral of u dv is equal to uv minus integral v du. Now, I use the serif here, the little tail on my u's, which I obviously don't on my v's. That's how you tell them apart. I could tell my writing apart, but obviously just want to make that clear. Okay. So we're choosing our u to be x and our dv to be sine. So what we do then is derive it, much like our u sub. Du is dx, and we integrate dv to get a v. So that means v is the integral of sine x dx. Well, that would be a negative cosine. So v is negative cosine x. Okay, so we have our u, we have our v, we have our du. We can plug it into our equation. Again, the integral is uv minus the integral of v du. So our u was x, our v is negative cosine x, minus the integral of v. Our v again is negative cosine x du. Du here being dx. Okay, so now if you notice, when we do our integration by parts, we always end up with another integral, and sometimes we have to do integration by parts again and again and again. But in this case, we don't have to. So I'm just going to clean this up a little bit. This is negative x cosine x. Negative and negative makes a positive. The integral of cosine is sine of x plus c. And that is our integral. Okay, so let's do another one. Ln x. Now, I just got done saying that generally we choose a u to be kind of our function that simplifies, and then our dv to be the other one. So essentially we have kind of two choices here. We either are going to choose u to be natural log of x, and then that means that dv is dx, or we could potentially choose our u to be 1 and our dv to be natural log of x dx. Okay, now the reality of this is that if we choose our u here to be 1, the derivative of 1 du equals 0, right? And essentially, we're really potentially like not going to get anywhere with something like that, but it is potentially a possibility. Now, the problem is if you were to try and find v, you are integrating natural log of x. But notice, well, that's what we're trying to do. So obviously that's not going to work. So if you're ever not sure, you know, try it. It's not a big deal. But notice we are integrating ln of x to get our v for our u sub, or our integration by parts, and that's what we're trying to solve anyway. So that's not going to do us any good. But again, we can also tell that because our 1 here was u. If we are going to choose 1 to be something, we often choose like just 1 dx to be our dv, and then the rest of it be our u. All right, so du then is 1 over x. Now the problem here is that obviously we like to choose our u to be the thing that's simplifying, but sometimes that's not really possible because like this, if we keep deriving, is actually not going to simplify. It's going to get worse and worse, but hopefully it'll work out. Now the v here, we integrate dx and we get x. Okay, so plugging into our formula again, uv minus the integral of v du. So u is, and v are x and ln x. I'm going to just write it like this so it's clear, but it's uv, so x ln x minus the integral of v x du. I forgot to add the dx here. So that's 1 over x dx. Okay, now, if we think about this, x times 1 over x is just going to be 1. So that's x ln x minus the integral of 1 dx. So the integral of 1 is x ln x minus x plus c. So that is our function. Okay, let's try another one. Alrighty. So again, something to note is that we are choosing to do integration by parts because u sub wouldn't work for any of these. So like, what would we choose a u for in this one? Like u is sine of x or u is x, that's the only real options. Neither of those would work because the derivative of sine is cosine, so we don't have a cosine to replace it with, so that's out. In the next one, well, again, if we chose x to be u, that wouldn't simplify, so ln of x is our u. We would need a 1 over x for u sub, so again, not possible. So essentially, we work with what we can do. Sometimes it's something trivial, sometimes it isn't, sometimes we have very particular methods we have to use. So, there's no real option. If we could use u sub, we probably would, because u sub's in ways, at least for me, I would, because it's easier for me. Okay, so again, we're going to use the same concept here where we go, okay, the thing that simplifies as we derive is our u. So u is x here. our dv, excuse me, is e to the 2x dx. It's the rest of it. Now, derivative of u is dx. Nice and simple. The integral of dv, the integral of e to the 2x dx is e to the 2x over 2. Now, if you don't trust that, we'd have to integrate this using u sub. So the integral of e to the 2x dx, when it's linear, it's not too hard for me to do in my head, but for your guys' sake, essentially what we do is we choose like our u to be 2x. So that means that du is 2 dx. So essentially we need a 2 in, we pull a 1/2 out, we have a 2 dx. So that's a 1/2 times the integral, 2 dx becomes du, and we get e to the u. Integral of e to the u is e to the u, and it's times 1/2. So that means it's 1/2 times e to the 2x, which is what I had here. So again, we technically are using u sub to integrate something like this, but you don't really have to use official u sub. If it's linear, it's pretty easy. All right, so again, it's uv minus integral v du. So u is x, v is e to the 2x over 2 minus the integral of v e to the 2x over 2 du, which is dx. So this is x e to the 2x over 2 minus, now here, same thing, integral of e to the 2x is e to the 2x over 2, and this is already an over 2, so I'll just pull it out in front. Again, same idea as if we need to use u sub again, we could, but we don't. We've already done it. So minus, we have 1/2 times e to the 2x over 2 plus c. So that is x e to the 2x over 2 minus e to the 2x over 4 plus c. Okay. Let's take a look at another one. Ooh, okay. So now square root x ln x. Which one gets better? Which one gets worse? Okay, with derivatives. The reality of this is that it's maybe not necessarily super clear which one to choose for our u in this case. But the thing to keep in mind is that it's better to try something and it not work out than for you to just sit there and go, but I don't know which to choose and not choose it. It takes less time to just give it a shot than it would to sit there and try and think about it necessarily like, oh, I don't know, this one or that one, this one or that one. They both, neither get better, right? Well, let's just use it in the order that it's written then. U is x to the 1/2, okay? So that means that du would be 1/2 x to the negative 1/2 dx. Over here, we would have like our dv then would be ln of x, which we just got done dealing with here. So notice we'd need like an integration by parts. So that's maybe not super promising. Okay, so instead, I'm going to just give up on that one real quick, and let's just try the other one, because obviously this is going to require an integration by parts, so maybe I'm not going to choose that one. And again, like I said, who cares? That took me all of about a couple seconds to realize that, no, I'm not going to try that one. I'm going to instead switch it. I'm going to say u is natural log of x. That means that du then is 1 over x dx. And then my dv is x to the 1/2 dx. And so my v would be, raise it to 1 by 1, so that's x to the 3 over 2 divided by 3 over 2. Okay, so now we can simplify this a little bit. So it's like saying times 2/3. So 2x to the 3/2 over 3, that's our v. Okay, so again, u v minus integral v du. All right, uv, so that is ln x times 2/3 x to the 3/2 minus the integral of v, which is 2/3 x to the 3/2 times du, which is 1 over x dx. Okay, so now we're going to simplify this a little bit. Um, this is x to the 3 halves over x would give us minus 2/3 integral x to the 1 half dx, because again, 3 halves over x here, that's like subtracting their exponents. 3 halves minus 1 is 1 half. So we have x to the 1 half. I'll write this in a little bit better order. 2x 3 halves ln x all over 3 minus that. Okay, so the integral of x to the 1 half, again, is x to the 3 halves all over 3 halves. So that's 2x 3 halves ln x over 3 minus this plus c. All right, so divided by 3 halves, it's like saying times 2/3. So times 2/3 and times 2/3, that's going to give us, again, 2x 3 halves ln x over 3 minus 4/9 x to the 3 halves plus c. Okay, so again, we're always ending up with like products here, but they're not just products. They're like a polynomial oftentimes. Okay, let's do another one. All right, x sine 10x. Okay, so again, same thing as before. Sine is not going to simplify, x will. So u is x, du is dx. So our dv, terrible dv, but whatever, is sine of 10x dx. So that gives us v is the integral of sine. So as a reminder, derivative of cosine is negative sine, so integral of sine is negative cosine, so negative cosine 10x over 10. Again, u sub here, it's a linear, so I can u sub it really easily, where if I were integrating this sine of 10x with u sub, 10x is u, and so on and so forth. Okay, so we can plug this in, uv, so x, and I'll put the negative in front, negative x cosine of 10x over 10 minus the integral of v du, negative cosine 10x over 10 dx. Okay, so integral of cosine is sine. The negatives, I'll add them together here. So we have negative x cosine of 10x over 10 plus, again, cosine is then sine of 10x over 10 over 10. So that's over 100. Let's see. And again, it's 1/10 pulled out, so it's a positive 1/10 integral of cosine 10x. So that is sine of 10x over 10 times 1/10. That's where we get the 100. Sorry, sometimes I take those things for granted as I kick my mouse. All right. Let me grab that real fast. Okay, next one. All right, so here we have something special. And essentially, we can kind of tell it is going to be, well, once you become familiar with it, you can tell it's special because of this squared here, x squared. Now, so far we've dealt with like linears, so x and stuff like that. But here we have x squared. Now, you're going to see what happens here. So again, e to the x is never going to simplify as we derive it, so it's clearly not our u. We're going to choose x squared. So u equals x squared. That means that du is going to be 2x dx, okay? Now we are going to choose our dv to be e to the x dx. So that means that v is e to the x. Nice and simple there. Okay, so our formula is uv, so x squared e to the x minus the integral of v e to the x times du, 2x dx. Okay, now, if we take a look at this integral here, x squared e to the x minus, I'll pull the 2 out, integral x e to the x dx. This is another chain rule, or chain rule, integration by parts. So sometimes we end up with, and you can usually tell it because you have some x to some power that's not 1 times something. You're often going to have to do multiple steps. If this was like an x to the 10th, you're going to have to do 10 steps. It's not going to be fun. So this is an x squared though. It's not too bad. So essentially, we are now worrying about this thing. So we choose our u again. U equals x, du equals dx. Our dv is e to the x. Our v, dx. Our v is e to the x. So we have x squared e to the x minus 2 times the quantity uv, so that's x e to the x, minus the integral of v e to the x du dx. So the integral we have here, that is x e to the x minus e to the x plus c in that parentheses. Okay, so now we can distribute this negative 2 throughout. We have x squared e to the x minus 2x e to the x plus 2 e to the x, and that's just going to be another plus c. So sometimes we have to do it multiple times. And for that, we actually have a method that kind of helps keep track of it nicely as we do this more and more. It's called the Tableau method. And I'll probably do a video on just the Tableau method. But the reality is that it's not necessary. And sometimes I find that while it's certainly easier, it kind of removes even more context from an already kind of contextless kind of problem where you're suddenly, it's kind of like the synthetic division or the reduced row epsilon matrix rules, where it shorthands things and it's certainly useful, but if you don't understand the baseline like concept behind it, it's not necessarily clear. All right. So let's do another one. All right, so again, cosine's not going to simplify, so I'm going to choose this to be my u. We also have the option of distributing cosine, which is always a possibility, but I don't think it's going to make our life any better, so I'm going to avoid it for the time being. But that's always something that I could maybe do. So I'm going to choose my u to be x squared plus 2x. That means that my du is going to be 2x plus 2 dx. Our dv here is cosine x dx. So that means v is sine x. Okay, so again, because we have a squared, it's very likely we're going to have to do this multiple times. So we have x squared plus 2x times sine x minus the integral of v sine x times 2x plus 2 dx v du. Okay, and it does look like that's going to be the case. Again, we can't integrate it in this form, so I'm going to do another u sub, integration by parts. Obviously, I do a lot of u sub, huh? Okay, so again, my u is my 2x plus 2. Oh, another thing is if you're doing it multiple times, you really shouldn't be changing what your u and dv kind of are. If I chose my polynomial here to be my u, I'm going to choose the new polynomial to be my u. I'm not going to switch it up, all right? That's never a good move. All right, sine x dx. So du is 2 dx. Over here, v, the integral of sine is negative cosine x. All right, so we have x squared plus 2x times sine x minus, I'm going to do parentheses around this, u, v, so that's negative cosine x times 2x plus 2 minus the integral of v, negative cosine x du, that's times 2 times dx. Okay, So my handwriting's getting worse. I apologize for that. And this one I'm getting a little sloppy. Okay, so x squared plus 2x times sine x plus, I'm going to write it in front, 2x plus 2 cosine x plus, so this is a plus here, and it's a minus here, so it's really minus altogether because the minus gets distributed. The 2 would come out, so we'll pull that 2 out. The integral of cosine is sine, so it's minus 2 sine x plus c. Now, as mentioned, there is a method to kind of help keep multiple integrations straight. So if you're doing like, this is like an x cubed, you'd have to do this 3 times. And it's really easy to forget your initial stuff. So I always write it down as I'm going. Otherwise, when I get to the bottom of just dealing with this, I'd likely forget it. So I'm not lazy about it. I do just keep writing it so I don't forget about it because it's really easy to forget. All right. So we have ln of x squared. Okay, so in this case, when we have something like ln x squared dx, well, this is kind of like an ln x times ln x dx, and perhaps we are going to use like 1 to be my u and 1 to be my dv. Unfortunately, we already know that the integral of ln of x is itself integration by parts, but that's not necessarily a deal breaker for us. So I'm going to choose my u to be natural log of x, and then my dv to be the other one, natural log of x dx. Again, a few things to know. I'm not going to choose ln of x to be like a u in the u sub concept because I'd need a 1 over x, and I don't have one. Okay. So derivative of u is 1 over x dx. The integral of v, we can either go back to finding it and following our steps that we've already done, which was here if we want. So we know it's this thing. That's one of the benefits, is that once you have learned something or used it before, you could certainly use it again. But it itself is a u sub. But I'm going to go ahead and copy this. A u sub, integration by parts. Gosh dang. All right, so it's something like that. I'm just gonna lose the C here. All right, so again, this is just pulled from one we've already done, but it's literally just using integration by parts. Okay, so let's go ahead and plug this thing in. We have uv, so ln of x times v, x ln x minus x, minus the integral of v du. So that's x ln x minus x times 1 over x dx. Okay, so the 1 over x will cancel out both of these x's, and we have minus the integral of natural log of x minus 1 dx. We still have this stuff, natural log of x times x natural log x minus x. Okay, so we can split these two things. So this is minus the integral of ln x, and this minus a negative, that I'm going to write that as plus the integral of 1 dx. We need dx here. I shouldn't be lazy. I should keep writing this one. ln x times x ln x minus this thing. Okay, the integral of ln of x, well, we've already done that several times. It's this thing here. So I'm going to copy that again. So we have natural log of x times x natural log x minus the integral of ln x is this thing. I'm going to draw parentheses around it, plus x plus c. So just doing a couple bits of cleanup here, namely distributing this negative. We have ln of x times x ln x minus minus x ln x plus x plus c. So we actually have a couple common or like terms here, and minus x ln x and minus x ln x. So we could certainly combine them if we wanted. So if we distribute this into here, this would be x ln x squared. Okay, then minus x ln x minus x ln x gives us minus 2x ln x plus 2x plus c. So again, I saved a bit of time by knowing the integral of ln x due to our earlier one, but it would just involve more integration by parts, which is kind of irritating. Okay, now here is a new problem. E to the x and sine x. Okay, now neither of these are going to get better as we integrate them or as we derive them, correct? So essentially, e to the x is just e to the x over and over again, and sine becomes cosine, becomes negative sine, etc., etc. So it doesn't really get better either, but it at least changes. So in that case, I'm going to try that to be my u. So u is sine x dx. I'm sorry, not dx, sine x. So that means that du is cosine x dx. So our dv is e to the x dx. So that means that v is going to be e to the x. Okay, so u, v, so that's, I'm going to write it as e to the x sine x minus the integral of v du. So that is cosine x e to the x. Don't ask me why I wrote it like that, but I did. Okay, so we've changed it a little bit, but now we have a new integral that we have to deal with, and it's still going to follow the same basic pattern. Again, e to the x, we're going to choose to be our dv, and this thing we're going to choose to be our u. So we have to do another integration by parts. So that is to say that cosine x is our u, and dv is our e to the x dx. Again, we don't want to go changing on it. So du is negative sine x dx, and our v here is e to the x. So we have e to the x sine x minus the integral, I'm sorry, minus the brackets here, u, v, so that's cosine x e to the x, minus the integral of v e to the x du. Sine x dx, and it's a negative, so right there. Okay, so this is e to the x sine x minus the integral, or excuse me, minus parentheses, cosine x. I'm going to write the e to the x in first. E to the x cosine x plus the integral of e to the x sine x dx. Okay, so now let's kind of just distribute this thing in a little bit. We have e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. All right, we're back around. E to the x sine x, we're back here. So that's potentially problematic for us unless we do a bit of thinking here, okay? So essentially, what we want to do is we want to find some way to kind of like replace our integral here. Okay, so we want to think of some way that we can kind of use what we know about this kind of process that we've gone through to go from e to the x sine x to get to where we are, to kind of simplify this, okay? So essentially, if you think about this, we started at the integral of e to the x sine x dx was equal to this thing. This is where we're at right now, correct? So essentially, we started here and we're here. Now, we've come back around, but that's not necessarily a bad thing for us, because what if we did a little bit of algebra? What if we added the integral of e to the x sine x dx to both sides? Well, these are like terms, so we can combine them as 2 times the integral e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x. But we didn't really care about finding 2 times it. We wanted to find just e to the x sine x dx. So divide everything by 2. When we get the integral of e to the x sine x dx, what we're looking for is just e to the x sine x minus e to the x cosine x all over 2. And obviously we still need our plus c. Can't forget that one. Easy to forget at this stage, but again, I'll just make some more room for it. There we go. So again, sometimes if we see a pattern, like if we ever come back to something we already started with, well, that's actually kind of beneficial for us. We just do a bit of algebra. So that's something that's really easy to forget. It doesn't come up super often, but if you were taking this class at like a university level, oh, they'd so give a problem like this if they were going to test on integration by parts. They'd so do that. That's just what they would do. So it's always these kind of problems that end up on tests for universities, but um, not necessarily for my class. But it's still an important thing to know. Anyway, so that is our integration by parts. And again, it's really important that you are proficient in integration by parts, just like it's important that you're proficient at USUB, because all integrations that we do will be one of these two things. But the hard part is determining which of those two, and like manipulating the function in such a way that we can then do one of those two. Anyway, thanks for watching.